Welcome to homework.
Okay, we have these tanks of salt water. This first one has 30 gallons of water, and at any time t, it has Q1 ounces of salt in it. At time 0, it has 25 ounces over here. Then we have this other tank that initially has 20 gallons of water in it, and it has Q2 ounces of salt. So that changes, the amount of salt changes as the water comes in. Initially, it has 15 ounces. So those two things are given there. Okay, this one has salt water coming in from somewhere else, salt water coming in from this tank over here, and then it's also sending salt water out. Okay, then this tank has water coming in. Water coming in up there. And then it's sending water over to the other tank, and it's sending water out onto the ground or in another somewhere else, and the other tank is sending water to it. Okay, so we want to make some differential equations that show the rate of change of salt per time. Okay, so let's use black. dq1 dt. Okay, so let's start here at the top. We got 1.5 gallons per minute, gallons in 1 minute, times 1 ounce per gallon. So that's going to give us ounces per minute. Okay, then we have this coming in. It's coming in at 1.5 gallons in 1 minute, and it has Q2 of T ounces of salt per 20 gallons. And then it's sending out this mix right here. So minus 3 gallons per minute. And how much salt is in it? Q1T ounces per 30 gallons. Okay, so that's sort of the strength of it. Okay, so let's get all the junk out of there. So we've got 1.5 ounces per minute plus 1.5 Q2 over 20 minus 3 Q1 over 30. So 1.5 plus 15 over 200, so 3 over 40. Q2 minus 1/10 Q1. So that's our first differential equation. Okay, now we have to write one for the other one. Oh, I need the picture though. I'll scoot it just a little bit there. Yep. We'll just have to move it up and down. Okay, dq2 dt. Okay, we have the fresh stuff coming in, 1 gallon per minute, 3 ounces per gallon. 1 gallon per 1 minute times 3 ounces per gallon. Plus, we have the water coming from the other tank, 3 gallons per minute, Q1 ounces per 30 gallons, 3 gallons per minute times Q1 ounces for 30 gallons, minus it's sending water out. I'm going to do them separately. Oops. So we have, there we go. So we have the one going this way, up, and it's going at 1.5 gallons per minute. And that one's strength is QT ounces per 20 gallons. And it's sending some this way, 2.5 gallons per minute times Q2 over 20. Or you could just send it out as 4 gallons per minute. It's gonna be the same. So this one we get 3 ounces per minute plus 1/10 Q1 minus 3/40 Q2 minus 2.5 over 20, so 25 over 200, 5 over 1/8 minus 1/8 Q2. So 3 plus 1/10 Q1, that's 540, so that's 8 over 40 minus 1/5 Q2. dQ1 dt, dQ2 dt. So those two equations Oops, this one really is just this here and this here. Okay, with these initial conditions, which are given in the book. Okay, then the next question is, find the values for Q1 and Q2 for which the system is in equilibrium. So it means where the rate of change of salt is equal to 0. Okay, so we're solving this system. 0 equals 1.5. You know what? I'm going to write that as 3/2. 3/2 plus 3/40 Q2 minus 1/10 Q1, and 0 equals 3 plus 1/10 Q1 minus 1/5 Q2. Okay, so I'm trying to solve this system. So first thing I'm going to do, get everybody in order, get all the fractions out of here. I'm going to multiply the first one by 40. So I'm going to have 4Q1 minus 3Q2, so I've moved them over here, equals 60. And this one, I'm going to go ahead and multiply it by 40 also. So I get 4Q1 minus 8Q2 equals, why don't I move them this way? Minus 4Q1 plus 8Q2 equals 120. Well, I'm going sideways here. Okay, so I'm going to add those together. So I get 5Q2 equals 180. So Q2 equals 5 goes into that 36 times. And then if I plug that in, I get 4Q1 minus 3 times 36 equals 60. 4Q1 minus 108 equals 60. 4Q1 equals 168. So Q1 equals 42. Okay, so when we get 36 ounces in the second one and 42 ounces in the first one, then the systems will be in equilibrium and they won't the amount won't change. Okay, now it says call those Q1E and Q2E and then make a new system of equations, X1 and X2. All right, so part C, X1 equals Q1 minus Q1E, which is this, and X2 equals Q2 minus Q2E, which is this. Okay, so then we want to make a differential equation, and so we're going to take some derivatives here. All right, so X1 prime is Q1 prime minus 0, because that's just a constant. Okay, Q1 prime, don't forget, was 1.5 minus 1/10 Q1 plus 3/40 Q2. Okay, now X1 was Q1 minus 42, and X2 is Q2 minus 36. So here I get 3/2 minus 1/10 of Q1, which is from here, X1 plus 42, plus 3/40 Q2, which will be x2 plus 36. Okay, so we get 3/2 minus 42/10 minus 1/10 x1 plus 3/40 x2 plus 108. Oh, let's reduce there. 9 will go in there. 4. Oh, no. 4 will go in there. 10. Oh, let's just leave it. 108 over 40. Let's get a common denominator of 40. So this one will be 60 over 40 minus this one times 4, 168 over 40 plus 108 over 40 minus 1/10 x1 plus 3/40 x2. So this one turns out to be x1 prime or dx1 dt, if you might want to make it look like that. Okay, those all cancel. Minus 1/10 x1 plus 3/40 x2. Okay, then we'll do the same thing over here. x2 prime will be q2 prime, which, if you'll remember, is 3 plus 1/10 q1 minus 1/5 q2. So 3 plus 1/10 x1 plus 42 minus 1/5 x2 plus 36. 3 plus 42/10 minus 36/5 plus 1/10 x1 minus 1/5 x2. Get a common denominator here of 10. 30 plus 42 minus 72 over 10 plus 1/10 x1 minus 1/5 x2. So x2 prime or dx2 dt is 1/10 x1 minus 1/5 x2. So notice this new system that we have is homogeneous, doesn't have any constants with it, as opposed to the one with q, which did. There you go.